David Wallace, welcome to the Uncertainty Podcast.
Hi.
How are you doing? You're in Pittsburgh. How are things going?
Good. Extremely cold at the moment, or just stopping being, but otherwise good, yeah.
Yeah, it's about, I think, 30 degrees here in Oxford. Comparatively speaking, it's not that cold, but I'm very cold. What is it in Pittsburgh?
At this point, about the same. It got down below zero last week, though.
Oh, yeah, no. No, thanks. So I'll take it. Although our heating broke last night. So actually the house is, I think most people would admit, very, very cold. So I'm doing my best.
Well, the thing about the weather in the UK is, by and large, if it's going badly, then your heating doesn't work or your clothes are wrong, then you're very uncomfortable. So
Yep.
I've discovered fairly quickly in large parts of the US, if you get the weather badly wrong, you die. So you have to pay slightly more attention.
You do, I know. I remember my first, I think, week in Oxford. It was in early October. And it was chilly, colder than I'm used to in New Mexico. And I thought I could get away with going outside without my coat. And about midday, I was outside Westgate, the mall here, and I realized I can't do this. I will die if I try to attempt this. So I learned very quickly the very basic responsibility of wearing a coat. Well, we're not here to talk about the weather. We're here to talk about quantum mechanics. So I have a big picture question for you, and it's one I asked Tim Maudlin. So I'd be curious to hear what you think. Is what is the difference between quantum mechanics and classical mechanics? What I want to zero in on is, like, what's the essential claim of a theory that makes it quantum as opposed to classically mechanical? You kind of see what I'm getting at there.
Yeah, sure. Okay, so, I mean, you can cover that in a lot of different directions. I mean, the most straightforward thing to say is that classical mechanics is the theory that works well to describe, well, what philosophers call medium-sized dry goods, matter sort of above the atomic or molecular scale, not moving too quickly or doing too many weird things, but that if you try to use classical mechanics to describe atomic physics or subatomic physics very rapidly, it simply fails. It gives the wrong answers, or it breaks down entirely. And so quantum mechanics is the theory developed to understand the behavior of matter when you go down below those success scales of classical mechanics. But in terms of conceptually what makes the theories different, I mean, classical mechanics, like the sort of norm in theories of physics really, says that, okay, this is how the system being studied actually is. The mathematics of the theory represents physical properties, quantities of the system, and the equations of the theory, the laws of nature, if you like, describe how those objective quantities and properties objectively change over time, and to some extent how they respond to interventions by outside systems. In quantum mechanics, it is, at least at first sight, extremely difficult to understand the theory in that kind of objective descriptive way. And you see this at the textbook level in quantum mechanics, because one of the first things you meet in learning the theory is an axiom of the theory that explicitly concerns measurement or observation. So in a normal scientific theory, then we tend to think the theory tells us what's happening objectively, and the question of how we measure what's happening is an important question, which might be answered inside the theory or it might not. But in any case, what it would be for another physical process to be a measurement would just be that it successfully records these objectively possessed properties of the system. You wouldn't expect to need to put axioms in the theory explicitly that said how measurement works. You'd expect measurement just to be more physics. And so the presence of an explicit call out to measurement in quantum mechanics is the tell, if you like, that something strange has happened and that we need to work much harder in understanding the theory than we had to for classical mechanics.
Well, could you say more about that? What is this axiom concerning measurement? Like, just to fill in the detail a bit.
Good, okay. So in quantum mechanics, there's a general principle called the superposition principle, which says that if the math of the theory, and I'm going to say this quite carefully, if the math of the theory can represent the system as, for instance, being in one place or being in another place, then it can also represent the system as being in both of those places simultaneously. or if the theory can represent the particle as going to the left or to the right, then it can represent it going to the left and to the right simultaneously. And one obvious thing one thinks there is, can we understand that kind of multiple representation as just cashing out some kind of ignorance of where the particle is? So can we understand the mathematical description of the system as being here and there at the same time as just saying something like, well, it might be here, it might be there, maybe 30% of systems like this are here and 70% of systems like this are there, or something like that. That turns out not to be viable. There's a phenomenon called interference in quantum mechanics, which says that you really, at the microscopic level, you need to treat these superposition states, these here and there at the same time states, not as probabilities, but as strange but objective descriptions of how the system is. But then you have the question of what happens when we look at systems prepared this way. What about if I want to measure where the particle is? And if the quantum theory is representing the particle as here and there at the same time, then what happens if I measure it? And the textbook answer is we change the game. Instead of objectively evolving these superposition states under the equations of the theory, we instead start understanding those superposition states probabilistically after all. So we couldn't do that originally at the microscopic level because of interference, but now we're being macroscopic. Suddenly we change our mind as to how to think about the quantum state, and we think about it as just assigning probabilities. So we do, after all, think about that here and there at the same time state as some probability of being here, some probability of being there, but when I look at it, I'll either find it here or I'll find it there. And that sudden reinterpretation of the state and the quantitative mathematics that goes with us and tells us what those probabilities actually are, that's the measurement postulate in quantum mechanics.
It's the postulate that tells you how to go from the microscopic description to the macroscopic probabilities?
Exactly. It's the axiom that lets us take one of these superposition states and say what happens when we look at it. Because again, your intuition, intuition is a terrible way to work out what happens if you measure a system, but let's go with it for the moment. Your intuition says if you measure a system that's here and there at the same time, you see a weird fuzz. But we don't, in fact, see that when we measure the positions of systems. We find them in definite places. And so somehow the theory needs to shift us from this weird indefinite state to a state that's definitely here or definitely there. And I think the most minimal way to think about that in the way quantum mechanics works is it's a kind of shift of how we understand the math of quantum mechanics from genuinely describing these objective non-classical superposition properties to non-representationally describing the system as just describing a probability distribution over possible positions or velocities or whatever property we care about.
When I took a course on the philosophy of quantum physics, the professor framed the different theories of quantum physics as taking as their point of departure their answer to the measurement problem, which I gather is just this question of what is actually happening when we make a measurement, like in the world, what is actually going on. Would you agree with that general framing that we get these different theories or so-called interpretations of quantum physics based upon different answers to that just really fundamental question of what happens at the moment of measurement?
Yes and no. Measurement problem is almost synonymous with how do we understand quantum mechanics.
Right.
And different ways of setting that problem up tend to privilege different ways of thinking about solutions to the problem. The way I would think about the measurement problem is the apparent failure of any ability to have a coherent understanding of what the theory is saying and how it's been made sense of. That is, at the microscopic level, we can't understand the theory probabilistically, and at the macroscopic level, we seem to have to understand the theory probabilistically. So, if you want to say, like, how can you reconcile those? One way you could reconcile those is you could say maybe at the process of measurement, some actually physically distinct thing happens. Maybe the equations of quantum mechanics break and are replaced by new equations, and maybe those equations in turn are microscopically statable, or maybe they irreducibly appeal to observers or conscious beings or whatever. But in any case, on that kind of family of ways of understanding or solving the measurement problem of quantum mechanics, you'd change the theory to a theory where the transition from superpositions to non-superposed things is a real physical process in the world. Another thing you might say is that the theory was incomplete, and that what we were doing when we made those measurements wasn't really measuring anything about what the math of quantum mechanics represented. We were measuring some other stuff, some hidden variables that the math of quantum mechanics left out. Other things still might try to say, okay, we don't want to modify the theory, we don't want to supplement the theory, what else can we do? And then some of those approaches might try to somehow read the probabilistic understanding of quantum mechanics all the way down, so that somehow, after all, we can think about there not being any sort of weird, non-classical, inherently quantum goings-on, even microscopically. Or you could think about it as trying to read the weird, inherent quantum mechanical stuff all the way up, and somehow reconcile the sort of apparent transition of the quantum theory into a theory of probabilities with the idea that really the dynamics of quantum mechanics carries on all the way.
Mm. It's at this point that people bring up the term interpretations of quantum physics, but I've been told on several occasions that it's actually an outdated terminology, that really these are different theories of quantum physics, quantum mechanics entirely. They're not just different interpretations of one theory. Could you comment on that? What is your take there? Do these approaches amount to entirely different theories as opposed to different interpretations?
It very much depends what you have, what a particular approach you have in mind. I mean, one way of thinking about the puzzle of making sense of quantum mechanics is that our normal scientific philosophy says take scientific theories as kind of literally representing the way systems are and how they behave. And our sort of standard physics says unmodified quantum physics is our best theory. And put those two together and you seem to have this sort of paradox of interpretation. We can't make sense of the theory, and it seems to involve this sort of irreducible call-out to measurement that's not defined in the theory. So your alternatives might be, I'll change my philosophy or I'll change my physics. So changing my philosophy might mean, okay, I'll change my mind about the idea that scientific theories are supposed to be representational. Maybe they're just sort of pragmatic tools for action. Maybe the logical positivists were right after all, and some kind of operational story. Or I could change my physics. I could say, well, the equations of quantum mechanics say that systems can exist in weird superpositions, and that's true even macroscopically. According to those equations, well, the equations of quantum mechanics must be wrong, or there must be some more to it than that. Changing the physics definitely gets you to new theories. It doesn't get you to any very successful theories, but it would definitely get you to new theories. Changing the philosophy, it's a bit subtler whether that counts as a new theory or not. If I've got the same underlying mathematics, but I want to regard it as some kind of operational calculus or pragmatic guide to action, is that a new theory or a different philosophy of science? I think that the devil's a bit in the details there.
So, making it specific, how would you characterize the difference between Bohmian mechanics and Everettian mechanics, the many worlds interpretation? Okay. Without biasing your answer on that, but between are those two different theories? It certainly seems like it. The differences between them are substantial enough that we're dealing with like two entirely different theories. But I don't.
Those are two entirely different theories. There is mathematics, dynamical equations in the Bohm theory that you don't find in unitary quantum mechanics, and which is the theory that is used in mainstream physics, and the Everett interpretation is very much an interpretation of unitary quantum mechanics. So these are definitely different theories. The equations change, and one tell that they're different theories is the empirical range of Bohm's theory is very small. It works for certain non-relativistic point particle systems. It's not adequate for phenomena involving light. It's not adequate for phenomena involving relativity.
Right. Okay. Well then, if you were asked, as you are being now, to explain the many worlds interpretation to an educated but still lay person, what would you say? How would you describe it?
Sure. Well, let's start again with the idea that quantum mechanics seems to describe systems as being able to have two sets of properties at the same time. And you might decide that that's just the microscopic world, and the microscopic world is a bit weird and we're not evolved to understand it. But then you ask, okay, if we measure the microscopic world, if we bring in a measurement device, well, measurement devices are just made of atoms. Quantum mechanics should apply to the measurement device as well. I'm made of atoms. Quantum mechanics should apply to me. What does quantum mechanics say happens when I make a measurement? And the answer is that quantum mechanics says that superposition infects the macroscopic world. So if my measurement device measures where a particle is, and the particle is somehow here and there at the same time, well, now the measurement device is measuring here and measuring there at the same time. Or to use Schrodinger's somewhat unethical example, if the way I record the particle being over here is that I kill my cat, and if the way I record the particle being over there is I leave the cat alive, then after the measurement, the cat is alive and dead at the same time. And that doesn't just seem counterintuitive, that just seems pathological and flatly in contradiction with our observations. And that leads to the idea that we need to re-understand the theory, or we need to change the equations of the theory. But if we don't do either of those things, we can say, well, why do we say it's somehow contradicted by experience for this to be what happens when I make a measurement? My intuition of what it would be like to be seeing a live cat and a dead cat at the same time is kind of like being very drunk, kind of like seeing double, seeing a sort of blurry double cat. But intuition isn't a great way to see how physical systems behave. Physics is a much better way. So if you ask physics what happens if I observe a cat that's alive and dead at the same time, well, it says that I, at the same time, am observing a live cat and am observing a dead cat. It doesn't say I am observing a weird cat. It doesn't say I have weird cat experiences. It says at the same time I have living cat experiences and dead cat experiences. And if you ask me what happened to the cat and I tell you, then you at the same time have being told the cat's alive experiences and being told the cat's dead experiences. And if you report on this podcast to your listeners what the result is, then your audience is now at the same time in a state of all learning that the cat is alive and in a state of all learning that the cat is dead, and if they put it on social media and so on and so on and so on. And all these processes are staying correlated. So again, this is just according to quantum mechanics, just according to the equations of the theory. Pretty soon after the measurement that killed or didn't kill the cat, then the whole world is at the same time in a state of the cat having been alive and in a state of the cat being dead. And by what I mean by in a state is in the state that quantum mechanics would assign to the system if the cat had actually been alive or if it had actually been dead. So you have this superposition now of two mundane classical goings-on, the sort of going on if a cat was killed and the sort that was going on if a cat was alive. All the quantum weirdness is in the claim that both of these are co-present in what the math is representing. But the interference effects that allow terms in superpositions to interact with each other are suppressed once we get to a macroscopic level by well-known dynamical processes called decoherence theory that we can study and model and test. And so in the absence of those interference effects, the two terms in the superposition, to use jargon, the live cat state of affairs and the dead cat state of affairs just carry on doing their own thing, not interacting with each other at all. So what the mathematics of the theory is representing is now not a superposition of things that can interfere with one another. It's a multiplicity of two separate things going on at once. And when we have two separate non-interacting things going on at once, that each of which separately incorporates the entire planet, then world is as good a name for any. And so hence the name, the many worlds theory. We have simultaneously present parallel situations, one of which in which the cat dies, one of which the cat lives. And I want to stress that this is something that happens if you just take the mathematics of the theory straightforwardly and representationally. I haven't said I can solve the measurement problem by adding an ontology of many worlds to an existing theory. I've said, if I think carefully enough about my theory, I realize it was a many worlds theory all along, and the measurement problem then dissolves. Because, after all, it was never the case that we had to transition from understanding superpositions as physical to understanding them as some kind of ignorance or probability. They remain physical all the time. And the fact that I see one set of outcomes rather than another is just a parochial matter. There's a version of me that saw the other set of outcomes.
Okay, let me ask some of the more metaphysical questions about this interpretation. I think the ones that would just occur to a layman. who's interested about these things.
Sure.
Where are these worlds? I'll give that as in a naive a form as possible. I think initially when I heard about many worlds, I had this idea that the universe itself splits at this moment of measurement or entanglement or decoherence or whatever. And then I thought of these different worlds as separate space-times, right? So that's why they don't interact. That's why we can't see them or touch them. They're just a totally different space and time. But I gather that's not correct. And so then you ask, if it's all just one space-time with all of these different worlds in some sense, where are they?
Yeah, so this is a little subtle, but as far as the best physics we currently have is concerned, which means roughly the standard model of particle physics that's tested in CERN and the Large Hadron Collider, according to that version of physics, space-time is not quantum. It's a background against which quantum processes play out. So the branching that happens when microscopic events get magnified up to the macro scale by quantum measurements or other quantum mechanical processes, those branching events happen in space-time. They're not branching of space-time.
Right.
So as far as that physics is concerned, where are those other branches? They're right here in the same room with you. Why aren't they interacting with you? Why can't you see them? Well, again, because the equations of physics tell you you can't see them. We don't use intuition to work out if I can see a physical object. We ask, does the physics model an interaction with it? And the structure of quantum mechanics tells us that these are parallel processes, they don't interact with one another. If you want a metaphor, these ideas are out of vogue now, but there was a point where people in particle physics started talking about shadow matter, which would be like there'd be shadow protons and shadow neutrons and shadow electrons, and the shadow particles would interact with other shadow particles, but they wouldn't interact, or only very, very weakly, with the non-shadow particles. And so there could be a shadow room all around you with a shadow podcaster sitting in it, and you wouldn't be able to see them at all. The way you do that mathematically isn't quite the same as the way it would work in Everett, but that gives you a sort of metaphorical idea of what's going on. The worlds are co-present, they're in the same space, but they're dynamically disconnected. That said, there's a subtlety. I said that's what our best current physics tells us, but our best current physics is wrong. We know that a satisfactory completion of the standard model of particle physics would incorporate gravity. We know that our best classical theory of gravity, Einstein's general theory of relativity, is not a theory where space-time is a passive background. It's a theory where space-time is a dynamical player. Space-time is dynamically influences matter and is dynamically influenced by matter. So a quantum theory of gravity would have to, unless somehow quantum mechanics itself broke down, would have to be a theory where space-time was a quantum dynamical player, and then we'd be able to have things like quantum superpositions of different geometries of space. And then, because matter curves space, curve space-time, you'd expect that if the cat was, you know that if the cat was dead, space-time would curve differently than if the cat was alive. That means that if the cat was alive and dead at the same time, then space-time would have to be curved over here and curved over there at the same time. And that would correlate, entangle, in physics terminology, the structure of space-time with the structure of matter. So in fact, that probably means that macroscopic branching events would also branch space-time itself, or the local bit of space-time itself. And so it would actually genuinely be the case that macroscopically different branches existed in their own bits of space-time. But that's speculative, and we don't have full control of the mathematics that would describe it. Insofar as we're just interpreting our non-gravitational physics, where space-time is a background, then the branching happens in space-time, not of space-time.
So that was going to be my next question was, given that we don't know how to integrate quantum mechanics and general relativity, so we don't have our final theory of a quantum theory of gravity, how confident are adherents to these various interpretations or theories in the actual truth of their framework, given that they know that at best these theories are approximately true, or better, they just don't know whether or not those theories will emerge from a quantum theory of gravity? Like, it's a general question of how confident can we be about our extrapolations from known physics, whether from quantum mechanics or general relativity, to that final theory? Like, does not having that final theory put a big question mark over every other claim in physics, or would you say no? I mean, I'm confident enough in a many worlds interpretation. I think that basic ontological dynamical picture will survive in a quantum theory of gravity.
Yeah, okay, yeah. Yeah, so it definitely doesn't undermine every claim of physics. I'm currently sitting on the 11th floor of a skyscraper. One of the claims of physics is that if I stepped out of the window of my office, then I would accelerate towards the ground and in short order hit it. I am extremely confident of that claim. I am very sure it's not going to be falsified by future physics. And we could go less strongly than even that. I mean, our physical theories provide extremely detailed predictive structure, which has been tested in many contexts to extraordinarily high levels of accuracy. It is implausible that all of this is a fluke. It is, I think, extremely likely that the mathematical structures we currently use to make predictions and model phenomena in the regimes in which they're well tested will carry on working. Now, what you want to make of that from a more philosophical point of view depends a little bit on how thick you like your metaphysics. I like my metaphysics pretty thin. I'm happy to say that if I understand how some part of the world is structured, and that structure is represented by the mathematics of the theory, then the way in which I cast those structural claims into language is not useless, but it's a sort of secondary task and somewhat pragmatic and somewhat tied up with intuitive understanding. What physics is really saying is, look, here is how this system is structured mathematically. I expect those structural facts largely to be continuous across theory change. It might be that those structures get incorporated into other theories such that they are only approximately correct and only hold in certain regimes, but they still carry on holding in those regimes. So, in the concrete case of a quantum theory of gravity, most attempts to combine general relativity and quantum mechanics, certainly most if measured by the number of people who've worked on them, tend to assume that the structure of quantum mechanics will be largely unchanged by the incorporation of gravity.
Right.
The string theory research program has this character, for instance. String theory is very much a quantum theory into which we try to incorporate gravity. String theory dominates sociologically quantum gravity theories, but most rivals to string theory are also quantum theories in this case. Not all, but most. All that the Everett interpretation requires is the abstract structure of quantum theory. So if any of these approaches to quantum gravity are correct, then the Everett story is, right or wrong, is unchanged by the move to quantum gravity. Even if, in fact, the mathematics of the sort of structures of quantum mechanics end up having to be modified by the move to gravity, I would still expect our understanding and interpreting of the theory in regimes where gravity doesn't matter to be largely unchanged. And the only caveat I'd say to that is that it's not always easy to tell which the regimes are where gravity doesn't matter. Maybe gravity matters when superpositions get macroscopic. So maybe when you try to create a superposition of me alive and me dead, then actually some process from quantum gravity comes in, and actually one of those dissolves away and only the other one continues. There are theories of that kind. I don't find them very persuasive, but it's not impossible. If that's the case, then I think the sort of baseline metaphysics of Everett would still correctly characterize quantum mechanics, but in fact, most of the macroscopic superpositions that make the theory sexy would go away. As I say, I don't think those theories are likely, and I think they're accepted only by a tiny minority of physicists. But that would be a case, I think, where theoretically the content of Everett continues, but you modify the dynamics in a way that takes away most of its surprising features.
Right. Well, so what do you mean when you say that you prefer your metaphysics thin versus thick? One interpretation is that you've spoken about the preserving the structure from one theory to another. And then you might think, like, are you saying that it's not particularly important to you how we fill out that structure in terms of what we think is actually going on in the world, like supplying concepts that fill these out into a concrete picture of what's happening in the world? Or how are you cashing this out?
Okay, so it's probably easier to use an example than try to lay out an abstract theory. So think about classical gravity. So the way Newton and, well, let's not get too far into interpreting Newton himself. The way people in the 18th and 19th century generally thought about gravity after Newton's work was gravity was a force. there was an absolute background of space and time. They'd sort of come to realize it was a bit more complicated than that because we couldn't detect absolute motion, but there was basically this sort of background of, objective notions of inertial motion, and against that objective background, gravity was a force, and gravity yanked things in that were far away via the inverse square law. And famously, of course, Einstein realized that we could think about gravity not as an objective force, but as a manifestation of a curvature in the inertial structure, the space-time geometry itself. That often gets described as like the move from Newtonian gravity to general relativity, but of course it was something Einstein realized about Newtonian gravity itself. He realized that you could understand it not as a theory of long-distance forces, but as a theory of local, I could say space-time curvature, that's a bit anachronistic, localizing of inertial structure with gravity, with matter controlling what the inertial structure is, and the inertial structure varying from place to place in a way that can look like a force to us. So those are two different ways of reading Newtonian gravity. So then, what I had in mind by metaphysics thin versus thick is, are those two different ways of thinking about the self-same scientific theory, such that the question of whether we think about gravity in terms of forces or localized inertial structure is a kind of matter of convenience and interpretation and communication and pedagogy, or are those objectively different ways the world could be that simply can't be distinguished observationally? In other words, is there a real fact of the matter as to whether gravity is a force acting on a flat space-time or a manifestation of the localizing of inertial structure of the curvature of space-time? Those sound like quite different words.
Yes.
They correspond to the same mathematics. Are they different ways the world could be, or just different ways of talking about the world? What I had in mind by thin versus thick is the thinner your metaphysics are, the more you're going to be willing to identify possibilities, and the thicker it is, the more you're going to want to say these are there are metaphysics-linked possibilities that we just can't distinguish through the methods of science.
So then you're saying if we have a thin enough conception of the many worlds theory, it's very likely or increasingly likely that many worlds will survive in a quantum gravity context, just by the nature of the case.
Yeah, I want to be clear. However thin your metaphysics is going to be, a commitment to the many worlds theory is still going to be a commitment to the fact that many different classical goings-on are simultaneously present. The way you might describe that in terms of, other branches diverging from each other or overlapping from each other, or do we think about individual objects as co-present in many worlds, or are there many objects? All of those kind of metaphysical questions, however you answer those, it's still going to be the case that there's a different version of me looking out the window at different weather and having a different conversation.
So, many people, when they first hear about this whole new vision, think it's crazy.
Really?
And that was my initial reaction. And I still feel that way, but I'm finding it increasingly difficult to maintain that attitude with intellectual respectability. So make of that what you will. What would you say to someone, me, that finds this a bewildering vision? This isn't really an epistemically relevant consideration for sure, but just from the standpoint of do you think there are things that actually could help someone to see this as a vision that's not super extreme or radical or crazy? It's actually more as close to intuitive as you can get in this circumstance. Anyway, what do you say to the person who says, well, this is just crazy?
Yeah. Well, look, it's not intuitive. There's no sugarcoating that. Intuition is not a good guide to truth in physics. Very little in physics is intuitive, and most intuitive things are wrong. You can develop and change your intuitions with practice. I think what I find intuitive in physics is not the same as what I found intuitive when I was 16, but
fair play.
Nonetheless, just the fact that we don't find something intuitive, I'd say is not even prima facie grounds not to take it seriously. Our intuitions are well designed for the activity of surviving on the African savannah. They're not well designed for situations that don't track that well, unless you've got some sort of theistic reason to think otherwise. But beyond that, I mean, so the two things I think you can say that somewhat sugar the pill, if you like. I mean, the most important one is just we have quantum mechanics. It's an amazingly successful theory. Contrary to what you sometimes hear in various corners of the philosophy space, we do not, in fact, know how to modify that theory, to change it in ways that reproduce more than a tiny fraction of the incredibly vast empirical data for it. So the evidence that quantum mechanics, as we characterize it mathematically structurally, is along the right lines. It's overwhelming. It's the best scientific theory ever, with the possible exception of natural selection. And Everett is really just an attempt to take that theory literally. As I said this when I originally presented it, but we're not adding the worlds to an existing theory. We're trying to make sense of the theory, and we're seeing that what the theory itself describes is this parallelism. The other thing, and this is a bit more metaphorical, it's worth saying that we're used to the idea that our world might be vastly enlarged by scientific discoveries that have very little direct effect on ordinary goings-on. So very, very little in our everyday lives on Earth is directly affected by anything outside the solar system. I mean, the only real exception is if you look outside and the sky is clear, you'll see lights in the sky. Even most of the lights you see are stars that are, within 100 light years and less. But on the basis of the sort of pattern of light coming from the sky, and mostly on the basis of aspects of the pattern of light coming from the sky that's invisible to our naked eyes, that's detectable only by increasingly subtle devices, we've conjectured a completely unfathomably large universe. I mean, I genuinely can't get my head around how far it is from here to the sun, let alone how far it is to the Andromeda Galaxy, which is the nearest galaxy, let alone how far it is to the edge of the known universe. And the edge of the visible universe is only the beginning of the whole universe. The visible universe has hundreds of thousands of millions of galaxies. Each one has hundreds of thousands of millions of stars. Most of those stars almost certainly have planets around them. Those planets have oceans. Those oceans have beaches. Those beaches have grains of sand. None of that stuff is stuff we have any realistic chance of seeing or engaging with or detecting. The bits of it that are out beyond where the speed of light can reach, we're not even in causal contact with. And yet we take very seriously the fact that we're very confident the universe is that big because of the success of the scientific theories that posit it. So in a certain sense, since the development of modern cosmology, arguably even since Bruno supposed that the stars were other suns, we've already been living in a multiverse, and it's unfathomably large. Quantum mechanics just makes it even larger.
So I actually agree with you with respect to the more mundane, like cosmological multiverse, but we'll return to this at the end. There's something about the Everettian many worlds that I find particularly disturbing, but I've made my peace with this just wider expanse of space that goes on and on. So we'll get back to that. But sure. You made this claim that quantum mechanics is one of the most experimentally confirmed theories that we've ever crafted. Okay, good. One of the chief objections...
I got the one, to be honest. But...
Oh, yes. One of the chief objections to Everettian mechanics is that it can't reproduce the probabilities involved in quantum mechanics, and like the probabilities of obtaining certain observations. We go and then we obtain those observations with that exact probability. This is great confirmation. The basic problem, as I understand it, is that in the many worlds account, every observation of an experimental outcome happens somewhere, right? So when there's a quantum experiment, the universe splits, and so there are both outcomes observed. And so in that sense, like, what does probability amount to in that situation? What does it mean to say that, this outcome has a 10% probability and this one has a 90% when both happen? Wouldn't that mean that it's like 50% probable? So that's the really rough and ready issue. Perhaps speak to what the problem is, but then why isn't that a problem?
Yeah, absolutely. No, I mean, this is the most philosophically interesting puzzle in Everett, I think. It's the one that I think conversely sheds the most interesting light on philosophical questions. So yeah, absolutely. There's lots of ways of putting the problem. You put it one very clear way. I mean, a different way to get a similar concern is it's critical in quantum mechanics that the theory makes predictions that are probabilistically characterized. Normally, our route to having probabilities in sort of objective world is either some kind of objective fundamental chance, whatever that means, or it's some manifestation of our ignorance about the exact microscopic conditions of something. So, paradigmatic examples, if I roll a die, we would normally say, well, exact knowledge of the micro condition of the die would determine where it lands, but I assign probabilities evenly because I don't have enough information about how it was rolled. Conversely, if a neutron decays or doesn't decay, and there's a Geiger counter clicks or doesn't click, that's our paradigm of a sort of irreducibly stochastic process. So there's no fundamental stochasticity in Everett, and while it doesn't suppose we know everything, then we're not ignorant of things that seem salient to the probabilities. So where do the probabilities come from? And there's sort of two answers you can give to that. As a negative answer and a positive one. Let me quickly sketch both. So the negative answer you might also call a sort of no double standards answer. And the negative answer broadly says, look, there's no problem formally with understanding where probability enters in the Everett interpretation. We understand exactly which part of the mathematical structure fixes the probabilities, and we understand exactly what the dynamical process is whereby that bit of the mathematical structure comes to have the synchronic and diachronic properties that probabilities have to have in order to play the role of probabilities in our theorizing and our confirming of our theories. So the question is really, how are we justified in interpreting a certain part of the math as probabilities? And there it's just not clear that Everett is worse off than any other concrete theories of probability we have, because what objective probability is in general is enormously mysterious. Roughly speaking, people have tried to make sense of objective probabilities as either being just brutally posited, or as associated somehow with the pattern of long-run frequencies in the world, or as associated somehow with the symmetry structure of the world. And all of those have severe problems. If you're just brutally positing probabilities, it's not at all clear that we even understand what it is that's being brutally posited. And the claim sort of reduces just to saying, well, these numbers are the probabilities, shut up and go away. If we try to make sense of frequencies, we tend to run into the problem that while frequencies seem to be how we observe probabilities, we run into circularities if we try to use the frequency to define probabilities, even at the formal level, let alone at the level of trying to say why I should trust the frequencies to guide my actions and to confirm my theories. If we try to ground probabilities in symmetries, then we run into the fact that something has to break the symmetry so that one thing happens rather than another. And so the negative response to Everett is just to say, well, there's a very general philosophical problem of how to understand objective probability. That problem is pretty intractable, as are many deep problems in philosophy, but the Everett interpretation is not obviously worse off here than single-world approaches, and this is another example of what was already a problem just being made salient by throwing into an unfamiliar context. That's the negative response. The positive response starts with a sort of loophole in what I just said about making sense of probabilities from an Everettian point of view. I said that if we had the idea that symmetries determine probabilities, we run into the fact that one thing has to happen rather than another, so something has to break the symmetry. Well, in the Everett interpretation, it's not true that one thing has to happen rather than another. The symmetries of a problem can be exact and persist through the process of making a measurement. And so that creates some logical space to try to ground probabilistic claims in claims about the symmetries of various dynamical processes. And there's been a tradition in philosophy of physics, from the 90s and 2000s mostly. David Deutsch did a lot of work here. I did some of the work here. Other people in Oxford and elsewhere did it. That basically says, okay, let's try to use those symmetries to make sense of the probabilities quantitatively. And the way those things roughly work is they start by operationalizing the notion of probability in terms of how we confirm theories and what our betting preferences are in a sort of familiar philosophical way. And then proving various kinds of representation theorems to the effect that on certain assumptions about how rational behavior works and certain assumptions about the physics, then all rationally non-contradictory strategies end up being strategies that are as if these numbers in the quantum formalism were probabilities. And so that gives you a positive route to understand probability that actually lets you say, well, maybe we understand probability better in the many worlds context than in the single world context. But the fallback position, if one doesn't buy that, is to say, well, we don't understand probability in the single world context either. So it's not a special problem.
Right. So you don't think the problem of probability, minus the positive answer, you don't think the problem of probability is any worse in an Everettian context than in just mundane context? You don't think it's any harder or more significant or of a deeper issue? It's just at the same level?
Yes, in that I think that all of the attempts to understand objective probability in contemporary philosophy completely fail, with the arguable exception of the brute strategy of just positing it, which you can do in Everett as well.
So a naive picture of probability in an Everettian context is to think that it refers to the number of branches. So that if an outcome by the equations of quantum mechanics is given a 30% probability and the other outcome is 70% probability, you might say, well, in 7 of the 10 branches, this is the experimental result you'll see, and then 3 of the 10, this is the one you'll see. And so then the odds are given the odds that you'll find yourself on one set of those branches versus the other.
Yeah.
I mean, that's all incorrect. So in that case, what does it mean to say that this outcome will result with, say, 70% probability? If they both happen, both branches, it's not as if what that means is that the odds that I will find myself on the branch that has this experimental result is 70%. Because depending on your metaphysics, like I split into both those branches. So there's no sense of like my soul being landed on one branch versus another, and these are just kind of the brute probabilities. Rather, like, what does it even mean now in this context?
So there are sort of routes where I could challenge the metaphysics and the semantics of that, but let me not go in that direction. Just stick with a fairly flat-footed understanding that, talk of what will happen to me doesn't really make sense. So I know I'm going to have multiple successors. I certainly can't count them. There's not even any well-defined metric of counting for branches. That's a sort of arbitrary how many branches we say there are within limits. I'm going to have a whole bunch of successors, and depending on actions and choices I make, things will go well or badly for them. The most sensible set of outcomes and choices here is really whether to accept a certain scientific theory or not, because we're really concerned with, does the probabilistic evidence that putatively confirms quantum mechanics actually confirm it? But you might also be a bit more stylized and talk about, well, I'm going to place a certain bet on the measurement giving certain outcomes. So we already know that we use the notion of bets as a sort of stylized way of understanding how we quantify probability, and we know that there are Dutch book type arguments that say that unless you analyze bets in accordance with the probability calculus, then you will reliably lose money. You'll be committed to something we all agree is irrational. There are ways of making those arguments much subtler, but that'll do as a starting argument. You can certainly run those kind of Dutch book arguments to ask, how would I react to a series of quantum mechanical processes? And you can basically establish that I'm more or less committed to assigning some distribution of probabilities over those branches, and choosing to maximize expected utility with respect to those probabilities, because anything else I try to do in this situation is just going to mire me in inconsistency. But you can go further than that, and you can say, well, because of the symmetry structure of the theory, and because I can sort of transform some bets into other bets by physically performable processes, then actually I'll be mired in inconsistency if I assign any old probabilities to branches. The only way I can avoid being mired in inconsistency is if I assign to branches the probabilities, or quote probabilities, because all they are things that get their meaning from the role they play in my rational action. The only way I can avoid miring myself in contradiction is if those quote probabilities match the ones that the quantum formula says should be the probabilities. So, in a sense, what the arguments are saying is, if you were stuck in a Everettian universe, and even if you completely resisted any sort of revisionary semantics or metaphysics to make it seem less weird, still you probably don't want to just sort of hide under the covers and gibber. You still want to sort of get on with things. What strategies exist to getting on with things, to behaving rationally, either as an individual or a community, or as a scientific research team, that are rationally consistent? And the claim is that the only rationally performable strategies, the only strategy you could actually really enact in a consistent way, are the strategies that treat the quantum mechanical mod squared amplitudes, the thing represented by the bit of the math that's supposed to be the probability, to treat those things as playing the role of probability. And in particular, in theoretical confirmation, the only consistent, coherent, performable strategies are going to be the ones where we regard things that happen with extremely low branch weight as tantamount to not happening, or rationally neglectable.
Interesting. We're at the limits of my understanding, so I have no more profound questions to ask about that. But when a branching event happens, in the most basic sense, what happens to the human person? You know, when I go to open up the box to check on Schrodinger's cat, and everything, and through decoherence, everything starts to split up, and there's now two me's.
Yeah.
Like zoom backward in time. So before I open that box, should we say that whatever I refers to, am about to cease to exist, being replaced by two duplicates that now split, or however many, given that we can't quantify the number of branches? Or should we say instead that, like, those two, simplistically, those two people presently exist right now here, but they're just overlapping? I mean, I think both of those answers sound bananas. So how should we think about the metaphysics of persons through time?
Yeah. So this is again a place where I think it's kind of a little bit indeterminate. This is the thick versus thin metaphysics again.
Right, okay.
I think those are both useful ways of thinking, and the mathematical formalism of quantum mechanics won't distinguish between them. The only caveat I'd say is that I think thinking about the splitting as you ceasing to exist and then recontinuing doesn't really get the psychology right. I mean, what it is, unless we believe in immaterial souls, what it is to physically continue is to be causally, structurally related to a successor. This is just a situation where you're causally, structurally connected to multiple successors. So there's a sort of problem of grammar in how you might talk about that. But in terms of the kind of thing that is normally seen as salient to us in continuing to exist in a physicalist universe, then those things obtain in the Everett setup. And of course, there's a fairly substantial philosophical literature and science fiction literature, indeed, on thinking about branching scenarios of that kind. And it's worth saying, of course, that one thing that can't happen in the Everett situation is you can't be in a situation of competing with your successor for resources, or having to share a causally connected reality with them. I mean, there's an episode of Star Trek in which constantly moves people around by having them broken down into their atoms and reassembled. An episode in which Commander Riker turns out to have been split into two copies, and then one of them's been stranded on a planet for a decade. And when they pick him up, it's a complicated situation, and they're competing for the same girl, and it makes the original, or the one we think of as the original Commander Riker, think differently about life choices he's made and so forth. And it's, as Star Trek goes, it's a good episode. But you notice the one thing Riker didn't think was, oh wow, given there were two copies of me, that meant I died on that planet. And actually I'm only 10 years, or rather, the person I thought I was died on that planet, and really I'm only 10 years old. I came into existence at that point. There's a sort of awkwardness of grammar, but I just don't think it's a psychologically coherent stopping point to just think about sort of branching where you're sort of causally disconnected from the other branch as tantamount to death.
So in that episode, is he split or is he cloned and then both of the two live on?
I'm not sure I know what the difference would be. I mean, the way the teletransporters work in Star Trek is that, I mean, they don't, of course, it's nonsense, but is you're disintegrated, the precise record of where all the atoms and molecules in your body are is sent through space, and it's then used to construct, I guess 3 equals mc squared, it's used to construct a new version of you of the same pattern. And what happens in this episode is the signal accidentally gets branched, so the signal gets up to the starship, but it also bounces off and gets to the teletransporter back on the surface, and so the transporter on the surface assembles a copy of Riker, and the transporter and the spaceship assembles a copy of Riker. So now there's 2 of them.
Right. Okay. Now I'm remembering this as one of the questions that they asked on the Chalmers-Bourget survey of philosophers was, would you get into the teleporter? I would not. I have a different instinct here, which is that would be my death. However, like unpalatable that may seem, that if you get into the teleporter and it disintegrates your atoms and then it reconstructs that same structure but with different atoms somewhere else, there's no continuity between the two. I'm gone. So I guess my question will help crystallize your metaphysics, which we might be talking past each other given this thin versus thick description. But phenomenologically, what happens through a branching event? Because my question is whether or not there's like one consistent phenomenological awareness or internal perspective through a branching event. And in that case, it becomes difficult to maintain this view that the two weren't originally there, but just overlapping. Like, how do we account for phenomenological continuity?
Well, the timescale in which quantum splitting happens is extremely short compared to any relevant timescales of neural activity in the brain. So there is no question of having some immediate experience of the process of branching. It's just happening too quickly. I mean, happening ridiculously quickly, unless you have some extremely wild philosophy of mind. If you accept really quite weak supervenience claims, then you'll certainly have no experience of branching. You have there exists a continuous, well-behaved stream of experience up to the point of branching. There also exists a continuous, well-behaved stream of experience after the branching in both branches. And in each case, if you ignore the other branch, then nothing particular interrupts, phenomenologically certainly nothing interrupts the process of continuity in either bit considered separately. So, I see why you say thin versus thick. I mean, talking about that in a consistent way certainly shows the advantage of the idiom where we consider multiple copies to have been co-present before the splitting. But, you could say the same about poor old Commander Riker. Ultimately, the physical facts are what they are in each case. I've got physical goings-on which would be described by the physical system as a phenomenal consciousness. And then after the splitting event, you've also got physical processes of that kind. And there's certainly no period of disquiet, because if there is, it would have to be corresponding to some neurological goings on, and there aren't any.
Part of it, too, will depend upon, I think, your theory of time, whether or not you think things endure or perdure. Does the many worlds theory require like an eternalist view of time or a B theory of time? I mean, I don't know that anyone's tried to make it work under a presentist ontology or an A theory. I imagine that's just because it's the minority view, if I'm not mistaken. But what are the metaphysics of time that are entailed by the view? Are there any, or is it compatible with either?
I don't think it forces anything about the metaphysics of time that isn't already forced by modern physics generally.
Right.
I mean, I'm fairly orthodox in that I think the post-relativistic understanding of physics is not friendly to atheoretic conceptions of time, and I'm not convinced about the metaphysical coherence of those ideas even prior to considerations of physics. But I don't think Everett makes things particularly worse there. In fact, to be honest, I mean, if this isn't my project, if you actually like thoroughly atheoretic conceptions of time, if you like the openness of the future, there are ways in which I think a branching Everettian Multiverse gives you some resources to play that game that you probably didn't have in a single universe. And you can certainly see connections and things between the sort of physically instantiated branching processes that happen in Everett and the sort of talk of branching space-times that turn up in sort of Pryor's tense logic and some of its development by Belknap and people. And for independent reasons, I'm not desperately sympathetic to those approaches at the time, but there's certainly a space in logical space for somebody who's both sympathetic to the A theory and sympathetic to the Everett interpretation. There's probably some interesting metaphysics to be done there.
Interesting. This is a bit of a curveball for you, but do you see any possible connections between multiverse explanations for cosmic fine-tuning and then the many-worlds multiverse? My rough and ready understanding is that, in fact, the many-worlds, as it comes to fruition in Everettian mechanics, just has no bearing on the fine-tuning debate because typically, or automatically anyway, there's no variation in the fundamental parameters in branch to branch, from branch to branch. Those are just replicated over and over, and so if one of them is fine-tuned for life, they all are. Do you affirm that basic irrelevance thesis, or do you think there's potential to explain fine-tuning in the many worlds framework?
It's a little subtler than that. So if you think how the fine-tuning arguments are supposed to work, they basically require two things. Firstly, some kind of random process that sets the apparent fundamental constants to lots of different values. So obviously, if the process sets them, they weren't fundamental, but the things that look right to us as fundamental constants are really emergent, contingent features of a underlying reality, and there's some kind of dynamical process that randomly selects them. And then that process has to play out many, 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 many times. So that you actually have an objectively realized multiverse, so that we can appeal to anthropics to say why I find myself in one of the life-conducive worlds, rather than just saying that there's only one world and it's almost certainly not life-conducive. So it's certainly true that our current extant best-tested physics, the standard model again, has its parameters in as fundamental parameters. That means the quantum mechanical process's randomness will have those parameters, the charge of the electron, for instance, having exactly the same value in every branch. Right. So in that sense, you're right. However, those speculative theories that lead to this distribution of parameters, insofar as those theories have anything more than just we make up the idea there might be such a theory, they're invariably quantum theories. I mean, the classic mechanism in mainstream physics is that we have some kind of string theoretic universe where different ways the strings can tangle themselves up leads to different apparent fundamental constants. So those are quantum theories. So if you interpret them a la Everett, then the random process of the strings getting tangled up in different ways becomes a quantum branching event.
Right.
And so you have Everettian branches in which different tanglings happen. So in that sense, the Everett interpretation would give you the multiverse that you require along with the randomizing process to make a fine-tuning, an anthropic justification of fine-tuning work. Now, that said, the kind of arguments people are appealing to here almost invariably give you a kind of spatially vast universe where even relative to a single Everett branch, very different quantum tanglings happen in different bubbles. And so even if you replaced Everett with some unknown dynamical collapse theory that was somehow empirically adequate for particle physics, then you'd probably still get your multiverse. And so you don't need Everett there. But it's interesting to note that you do get it that way. And if you want to speculate a bit, and a few theoretical physicists have tried this game, there is something a little inelegant about having these two independent mechanisms of branching, particularly since they all look kind of boringly identical. So on the one hand, if we live in a sort of vast, spatially vast universe with lots of different bubbles, then pretty much every Everett branch looks the same as pretty much every other Everett branch from a universal point of view. They're just a whole bunch of statistically distributed bubbles. And likewise, if you think about the vast spatial extent, you concentrate on one bubble, and then you think in quantum mechanical terms, well, every bubble is a branching multiverse, and so all the bubbles are the same as all the other bubbles. And so there's some sense, the sort of developed physics intuition that gives you a sense for inelegance in theories makes you think that feels a bit inelegant, and so maybe there's some duality way of seeing this that doesn't regard these as just independent. And people have played around, but we're now on the speculative edge of theoretical physics rather than a philosophical thesis.
Well, turning towards a more philosophical bent on all of this and big picture life perspective, do you think that the truth of the many worlds interpretation should make any difference to the way people live their lives? I think it should, but what do you think? I imagine you'll say no, but I think the rough and ready idea where someone might disagree with you as to why they disagree is, if everything that can happen consistently with quantum physics does happen, if there's a branch where I make the opposite decision to every single decision I take myself to have made, it kind of looks absurd. The whole picture seems to lend itself to absurdism. And for me anyway, that's the truth as to why I still reject it. It's just because I think it is right next to that. It's one step away from absurdism. Do you agree?
No, as you correctly predicted.
Okay.
But it does depend on your meta-ethics. And I do think there's some interesting work, again, to be done here. So, at some level, there's something a bit logically weird about a situation where one finds one's way to absurdism or nihilism off the back of some discovery in fundamental physics, however bizarre the discovery is. And after all, if you think we have our moral sense because it was literally handed down to us in tablets of stone from a creator, then I suppose anything could go. I mean, then we just have some totally certain theoretical facts about ethics as a starting point. Putting that kind of thing aside, the epistemology of ethics is obviously extremely vexed, but a lot of its starting point is just sort of paradigmatic things we agree are good or bad, burning babies, to pick the usually callous example. We don't think it's bad to gratuitously harm innocence. It's good to reciprocate love. It's good to keep commitments, whatever you like. All of the we kind of build structures of ethics on a whole bunch of different meta-ethical approaches of kind of starting data of that kind. If you have an anti-realist ethics, then somehow the behavior patterns of this kind of thing are just constitutive of what we mean. If you have a realist ethics, then somehow we have some kind of metaphysical ampliative route that takes us from that starting evidence to these truths. And all of that could lead you to counterintuitive ethical conclusions in specific places that are very counterintuitive, that are very exotic relative to the paradigm situations in which we discovered our sort of ethical evidence. So maybe we can be led to, I don't know, take seriously the suffering of non-human animals or something, because that follows from our sort of trying to theorize around our paradigm ethical cases. But it's hard to see how any ethical theory we constructed there could withstand falsifying all of its classic paradigm cases. So if we live in a branching multiverse, then the instance of reciprocating love and meeting obligations and choosing not to burn babies, all of those things happened in a branching Everettian universe.
Right.
And so you can imagine a situation where the gods or the space aliens turn up and they say, humans, you're not living in a branching multiverse. That's not true. Everything's been happening in a single universe. But bad news, we're about to transport you to a branching multiverse and ask you to cope. It's coherent in that situation to think that somehow we would have to be ethically nihilistic if we went there. I don't actually think that's psychologically plausible. I don't think it's what we would do, but you can see the coherence of that. We'd have a set of ethical intuitions and ideas developed on a certain metaphysics that we would then be which was true metaphysics, but then we'd be transplanted to an utterly different metaphysics, and you could see how that could change things in principle. It's difficult to see how you get off the ground the idea of that we could just somehow have to abandon our entire ethical framework, including the paradigm examples that we built our ethical theory on, because of a discovery of this kind? I mean, if you want a sort of philosophy metaphor, there's twin. You can cut this if it's too technical. The sort of twin Earth experiments in metaphysics.
Yeah, in terms of sharpening your intuitions about theories of reference and like
that kind of
H2O
thing, yeah.
and then XYZ.
Exactly. So Putnam says, and Kripke, they have this idea. I forget exactly where the ideas come from. The liquid on water is H2O. So the liquid on twin Earth, even though it looks like water, tastes like water, it's not actually water. And if you were transported to twin Earth, the stuff in the taps there is not H2O, so it's not water. It's XYZ. XYZ is not water. And fine. I mean, you can debate the validity of those ones, but here's something that they didn't consider. Suppose actually, and this is in my book, suppose there'd been an international conspiracy of chemists, and actually the stuff in the taps had been XYZ all along, and anyone who did a chemistry degree was inculcated into the conspiracy, and all the evidence was falsified, and all the textbooks were falsified. Do we conclude in that situation, oh right, well, since water is H2O, I guess the stuff in the taps and in the oceans isn't water? Presumably not. The conclusion is, yeah, water was water was in fact XYZ all along. We were just wrong. Water was H2O. The point is that you shouldn't be holding on to a theory if it invalidates the basic starting data points that set up the theory in the first place. And that's true for a sort of metaphysical or metaethical theory, I think, just as much as it's true for scientific theory.
Connect some of those dots for me, because it's not immediately obvious. We're left with a situation where this branching Everettian picture seems to call into question the fundamental sources of value we take ourselves to be acquainted with. Because everything that can happen does happen. Every instance of moral good, we know there will be the corresponding instance of moral evil and depravity on another branch somewhere. Both outcomes will happen. Every outcome will happen. Mm-hmm. Your claim is then that does nothing to call into question the validity of our kind of fundamental ethical intuitions. Is that the basic?
I think it doesn't do anything to call into question the validity of our basic starting point ethical judgments. So, why is it bad to kick a kitten? That's not really something one derives from an overarching theory set. One might be led to conjecture utilitarianism or consequentialism or some deontological ethics from starting points like it's bad to kick kittens. But the epistemology starts with banal ethical observations that we basically mostly agree on, and reasons its way to superstructure. We don't just start knowing by the natural light that we should maximize utility, and thus infer the fact that it would be net low in utility to kick a kitten. So what I'm saying is that if you start with basic banal ethical observations like don't kick kittens, you build a theoretical framework on that basis, then somebody in a physics lab tells you something surprising about physics, and as a consequence of that, you decide to drop your previous assumption it was bad to kick kittens. Something has gone terribly wrong epistemologically.
But it's still epistemically possible, whether in physics or philosophy, to encounter something which calls into question the truth of those postulates, right? Because otherwise, it seems like you're saying that it's impossible to ever have an argument for moral error theory, for example. The idea that all of our fundamental moral beliefs are just false. I mean, I don't know that I could rule that out in principle, but it seems like the kind of considerations you're sketching would say that it's just impossible for any theory to give us that kind of conclusion, given that they're just the basic postulates that we started from. But it's like, well, no, I mean, it's an open question, I guess, whether these arguments for error theory succeed. Does it kind of make sense what I'm
I mean, look, I should caveat that I don't work in ethics, and if I have intuitions here, they're pretty anti-realist. But with that caveat noted, I mean, sure, you can imagine, you can certainly imagine reaching a sort of general moral nihilism. you can even imagine a situation where you're a robust moral realist. You think there are objective moral facts, and somehow your immediate responses to banal moral judgments are excellent but defeasible evidence of those moral facts. I mean, if you imagine, if you accept moral realism, you can also accept the existence of people raised in utterly depraved situations, and on the back of that, being led to profound error about the objectively real moral truths. What's harder to see how you could get to is to not simply accept the possibility that your entire moral community is in moral error, but to actually conclude it is in moral error as a consequence of some objective external world facts. And in systematic moral error, I don't mean in like isolated points. You can obviously see how your community could revise isolated ethical principles against the backdrop of its main ethical framework. You could see how could decide to admit children or non-human animals or whatever into our ethical circle or something. But it's hard to see how what would be an epistemically non-self-contradictory route that leads us not just to acknowledge the possibility that we're all in systematic moral error, but to actually conclude that we are all in systematic moral error. I mean, it seems to me that the thing that leads one to that is to privilege an intuition that one formed on the basis of a false metaphysics over the original judgment cases that were the beginning tools of your developed intuition.
So my concluding question stems from the name of this podcast, the Uncertainty Podcast. So in my efforts to not end a question on a preposition, of which of your philosophical commitments are you most uncertain?
It's a classic example, I think, of a sentence which is barbarically harmed by not being ended in a preposition.
I can't do it. I don't know why.
I mean, it partly depends how you define philosophical. I mean, I could talk about how confident I am in quantum mechanics. I'm pretty damn confident. I'm more confident in quantum mechanics than I am in the premises of my main philosophical theses. So I suppose those, the answer is definitely not quantum mechanics. Right. Maybe it's some of those frameworks. I think there's lots of space for good philosophy to be done on a lot of these sort of metaphysical, epistemological, decision theoretic, even ethical questions in Everett. So I am inclined to think that the way to understand probability in Everett is through the sort of broadly symmetry-based decision theoretic routes I sketch, but I'm much less confident of that than I am that the probability does make sense in the Everettian framework. I mean, in a sense, that's just logically entailed, obviously, but I'm substantially less confident that it would be the case. I'm not very confident at all in the things I was just saying about ethics, because, like I say, it's not a space I work in. I think those would be interesting questions for people to play around in who did work in it. That's probably enough to be going on with. I'm not sure I could rank order all the things I'm tenuous about.
David Wallace, thank you for coming on the podcast and having this interesting conversation with me in my efforts to become a budding philosopher of physics. These questions are complicated, and I'm marginally more open to the many worlds interpretation as a result of this conversation. And I can freely admit that my consternation and resistance is mostly all rational, but it's still very real. So I'll continue to think about these things. But thank you for coming on today.
Well, you're far from alone. Thanks for having me on. It's been a pleasure.